Okay. I share my screen. I guess I'm not. So I think exciting. It is the end, and it's basically we're just going to race through. I'm getting tons and tons of questions. This is great. Some cases it would have been wonderful to have these earlier, but I know everyone's studying now and finding stuff now. So this is one question I got from Megan is, can we do a few of these? The answer is yes. Yeah, we absolutely can. We'll go through this because I want to sort of talk through how to go about this kind of problem. So this is all about puzzle solving. Okay, we'll take a look at that one then. Where can we find this? This question was in a practice exam. This is in the final parts of the practice exam. So it's actually kind of low resolution on my screen. And because what I'm going to do is I'm actually going to exit that and then I can zoom in. Maybe do a little bit better this way. So what we have here is we have some structures, a whole lot of empty boxes, and a whole lot of marks. I'm going to be drawing a bunch of new ones of these this year because these ones are compromised. And the overall idea is you need to fill in the boxes. So you've kind of got the information. You need to just put this together. So this is in the practice final. I don't know if somebody has that more readily available than I do for what question number this is. Anyways, I'm going to start working through this. So what we're always looking to do is see if you can find the right information, and you need to think about this. So where can you start? You can start anywhere you want. So one thing you can look at is there's sort of a box of things over here on the side that are kind of dealing with something, and they're all isolated. And we have some information we're going to need to fill in others. So the question, for example, is what happens when I treat this is a BR, when I treat that with sodium hydride? Okay, thanks guys. Number 43 on the exam. I like this question because it sums up so much of the chemistry we've covered in the class. So this essentially is going to be doing exactly, Alyssa's right, it's going to make a triple bond. Okay, so then that's cool. Then this box here is saying, how do I go from this to this? So there's a single bond there. So you need a reagent that's going to reduce the double bond without touching anything else. And so you can use the hydrogen palladium on carbon that reduces double bonds to single bonds. Then what happens if I treat this bromine molecule with potassium T-butoxide? Why does it make a triple bond? It doesn't need to elimination. It's a strong base. And you can make the triple bond by eliminating hydrogen. Yeah. Yeah, so you're going to get a double bond. Thanks, Alyssa. So it's kind of similar to this guy in the bottom right, except it's got no bromine. And then basically this line is basically finishing off, how do we get from the triple bond to the double bond? I can use the Lindlar catalyst because that reduces double bonds, but triple bonds to double bonds, but doesn't do anything else. So this network all kind of fits together, and because you kind of link things in, it all needs to make sense. So this makes sense. You can go to this, and there's a one reagent way of doing it. So normally there's a way to check your work whenever I give one of these kinds of questions. Just going to use a finer tipped pen. There we go. Switch to black. No, red. It'll jump out better. Okay. So now the next question coming along here is what happens when I take this triple bond and I use a strong base like LDA? Yes, it's palladium carbon. Yes. Will we get network this long in a final? Yeah, this was from a final. The year I taught this one, I used this one first here in 2018, and the average mark was really pretty good on this. And it's the same lecture stuff you've received. And I'm sure you're as good as those lazy ass son of a bitches in 2018. You're going to deprotonate, exactly. Okay, so we've generated an alkyne. Now, if we look up here, this is saying A plus C goes to this. So this gives us a clue of what A could be. Because if we're doing this see, we're kind of doing retrosynthesis. So we're doing this disconnection. We're going to break that. The rest of A needs to be pretty much intact. And I'm making it a little bit harder because we know that A is related to this molecule D here. Something happened to it. We're able to make A. So A is not going to be that different from D. And so we can get this plus a ketone would give us this guy up here. And then this is saying I can make D. From D, I get the product A and ethanol, which is that. And if we're following along at home, which I guess you are, that's a cleavage here. So that's just ozone. The advantage you guys have is compared to the 2018 class that had this exam is you don't need to memorize all this stuff. You can actually have tables or pages or whatever you want listing different reactions and different things. So if I then take this guy and I use a catalytic amount of acid, 0.01 equivalents of HI, so it's a tiny amount of HI and a ton of pentanol, 100 equivalents. What am I doing? A little bit of acid, lots of alcohol. And is there iodine in the product? Yeah, adding pentanol. No iodine. Dea, you said ester. I think you mean ether. No carbonyl. It's a Markovnikov addition of pentanol. It's acid plus alcohol. So it's going to be a Markovnikov addition of the pentanol. And we know we're going to regenerate. We only have catalytic HI, but there's going to be a H plus. And like that's going to temporarily be there, and that's going to regenerate my acid. So I only need a catalytic amount of acid. Cool. So that's kind of filled out that side of the box. Then the question is, okay, how do I get from D to this? So what you really need to be asking yourself is, what the fuck just happened? And you're looking at it going, okay, it was a Markovnikov addition of bromine to a double bond. That's what happened. So how do I do a Markovnikov addition of bromine? And I think this is the right way to think about it. It's like, what is the reaction that happened? What reagent gets me to that reaction? Exactly, Alyssa, HBr. Perfect. Okay, I treat that with potassium T-butoxide. What happens? Yeah, Hoffman elimination. And one thing, E2 Hoffman elimination, right. And one thing that's clearing us and doing that is you can always check what's further ahead and see how you can tie things together. So you're like, oh, suddenly like there's extra carbons here that aren't in the product, like I did something wrong, or my functional groups have moved to the wrong spot, I might have done something wrong. Like the thing that clues you in that's a Hoffman elimination, besides it being a Hoffman elimination, because that's what the reagents do, is the fact that if you look at the product down here, you need to functionalize that carbon. And if you did an elimination of any other carbon here, you wouldn't do that. So you'd be screwed. The other reason we have a pretty good idea is going to, oops, I shouldn't have moved the background molecule. The other reason we have a pretty good idea that it's going to be a double bond is suddenly we're seeing MCPPA, and we've seen that react with double bonds. Spelling is not required by typing. Emily, so you're lucky. So what we have here is what happens if we treat that molecule with MCPPA followed by HBr. So again, you have to ask, what does MCPPA do? Epoxide formation, epoxide opening under acidic conditions. Perfect, yeah. And Melitza. And Alyssa says 2 OHs, and you're not right, Alyssa. It's going to be an OH and a BR. If we had opened it with water, it would have been 2 OHs. But we didn't open it with water, we opened it with a strong acid. So we make the epoxide. There's no points for the epoxide, and we open the epoxide under acidic conditions. And that's going to open it such that the carbocat, like the temp, if we draw this in, you're going to have the big delta plus at this carbon, the little one here. So under acidic conditions, your bromine is going to attack the carbon with the more positive charge. That's why I really am glad somebody asked this question, so we can go over a lot of chemistry today really quite quickly. Cool. Okay, then how do we get down to this thing down here from here? What do we need to do? So how do we get there? Perfect. We're doing an anti-Markovnikov addition of water. You take a look and you go, that's anti-Markovnikov. So I need to use my anti-Markovnikov water conditions. And I look on my little table of things that my cheat sheet, if I haven't memorized it, and it says I use borane followed by hydrogen peroxide and sodium hydroxide. Okay, I'm going to leave the bottom two boxes there for a second because they're the asshole bonus question. We'll go up here. So what we're looking at here is we're going to walk. We can basically walk around this network at the top. And what it says is from B, whatever B was, I treated it with ozone, followed by DMS, and I got A and butanol. And I wrote a note basically saying, what I mean is you get butanol and compound A from the top arrow, and you get ethanol and compound A from the bottom arrow, because this is a little bit confusing, so I felt that a note was required. And if we remember what butanol looks like, it's that. So what this seems to be suggesting is that you have an ozonolysis, and that initially, you know, if you reverse the ozonolysis, you'll have this carbon attached to this carbon. So B was likely, and you can pencil this in because we haven't locked this in yet, but we're going to be able to go around the other side and sort of see if everything makes sense. 1, 2, 3, 4. So we suggest that that's what B is right now. And if we then look up, like higher up, it makes this all makes sense. 1, 2, 3, 4. If we look at this thing, it ties into what B is, and you sort of check your work. So if you treat this with isopropanol in heat, is B a reasonable product? Yeah. And then there's a box because there's another product formed. Any suggestion? Thanks, Jesse. or Mackenzie? It does. I just said that, didn't I? And then I drew the other thing. Okay, so I don't get full marks for my own fucking assignment. Yeah, no, of course, you're absolutely right. Yeah, sorry. Everyone who was confused by what I drew there, you were all absolutely right. I even said that's the more positive place, and that's where the bromine attacks, and I promptly drew the wrong thing. Exactly. There we go. So double bond flip from Malitza, you're right. Dea said it was Zaitsev, and there's not really much of a difference. They're both basically the same, so why would you get one over the other? You don't, you get both, which is why you get both. And there's 2 boxes, and the marks are there. Okay. Sweet. Now, we've tied that in. We could guess at what was going on here. That looks like a reduction, and we have this guy over here. So what we want to do is we want to turn this through something into something that when reduced becomes this. I think these are the 2 hardest boxes on this system. Any ideas? Yeah, we need to get rid of double bond and write one. One equivalent of HI. Exactly. So if you fill out one box wrong, does it make the other box? So no, if you follow through and your logic makes sense, Gabriella, you'll get points. If what you do is you take everything and you turn it into bromomethane and then promptly do all your reactions on bromomethane, you're kind of making a question. If you're making a question far easier than it is purposefully, you will not get the marks. But if you make a mistake, you will. The thing is that most of the way, like, there's enough structures drawn in here that you can always catch yourself. So it kind of resets on its way around the network. You're not going to get completely fucked. Yeah, so a Markovnikov addition of HI first, and just one equivalent, not 2 equivalents. If you just add one equivalent, it's going to go to this one because it's the more substitute double bond. So you're going to form that one first. That one's going to react first. This is going to make the more stable carbocation, so it's going to react first. Then this suddenly got easy, right? And so of course you reduce that, you get that. So that all follows. Okay, so we got 2 more boxes here. Sodium ethoxide gives us something that we can reduce with Lindlar to that. So what do you think we're getting? This one's on the easy side. Thing to remember is this is one of those really good leaving groups that we saw. Perfect. There. Sites of elimination of the tosylate group. It's related to the triflate, but it's not triflate per se. And then Lindlar again takes your triple bond down to your double bond. What happens if I treat this with hydrogen and palladium? Yeah, going to alkane. Lose everything, right? Knock everything down to nothing. Benzene doesn't get destroyed. You need a lot of pressure to do that. But everything else just becomes 1, 2, 3, 4, 1, 2, 3, 4. Becomes an alkane. Okay. Now we can return back to the nasty questions. So AIBN and bromine. This is, there's no double bond, right? So there's no addition to a double bond that's going on. Radical, exactly. I love your enthusiasm. Where's the radical going? We're brominating, and I point out intermediate has one bromide. So there's one bromine going on there. Where's it go? There probably should be heat. It's AIBN. You're right. Amanda, I'm going to give you that. I should have written heat under here. No one's actually ever asked me that, Amanda, so good idea. You're absolutely correct. Next to phenyl, where the OH is. So you're saying right here, Hannah. Yeah, you get 0.2. I'll mark it down, Amanda. Or no, 0.5. You corrected assignment. Yep, you're absolutely right. Shit, where the hell have I put these? There we go. So, why are you saying that, Hannah? Why is that a good spot for the radical? Sorry, give me a quick second while people think about this. One of Hannah and Dea is right. Okay, so we're coming up with the next to phenyl. You get more resonance available next to phenyl. I agree with all of you guys. There's no resonance on that carbon next to that OH. It's tempting because it's oxygen, but the oxygen's already using all of its bonds. You can't draw a resonance structure. We'll try and use 5 bonds if it does anything. You can't do it. The next best spots are the tertiaries, but there is a one that is right here that can resonate in with the phenyl. That is by far the most reactive radical position. By far, because of resonance with the phenyl ring. So that's where we're going to generate our bromine. Okay, and then sodium hydride. Okay, perfect. Yeah, no, Hannah, it's really easy, and until you mess it up and do it, you can't see that it doesn't work. You have to screw it up first. So now's the time to screw it up because it doesn't count for anything. Perfect. Melitza saw that. You get a ring. It's really easy to think, ooh, elimination, but no, you get a ring because acid-base reactions with acidic protons are fastest. That gets an O minus. The O minus is exactly 1, 2, 3, 4, 5, 6 atoms away. 6 is the magic number. 5 and 6, it's perfect. It makes a ring. And we have that. Sorry, methyl group's on the wrong carbon. There. So that fills out this chart. We've done it all. Covered a lot of the chemistry in the class, talked about a bunch of the concepts that we covered, but a lot of this is just puzzling through stuff. Can you show what makes a ring? Yeah, absolutely. So, So sodium hydride takes off that hydrogen, you get the O minus, and then it's 1, 2, 3, 4, 5, 6 Sn2 onto the carbon with the bromine. It makes a ring because it can make a 6-membered ring, and 6-membered rings are everybody's favorite. Acid-base reactions are fastest. So before this does E2, before this does E1, before this Sn2, before the sodium hydride does anything, it looks for the most acidic proton. It's not on carbon, so it's not an E2. If there was no OH there, an E2 would be the right answer. But there is an OH there, and it's going to take away that hydrogen first. That might take you maybe 25 minutes. I'd expect half an hour. I budget about 40 minutes for you guys to do it, because there's a lot of stuff in there. The exam is 3 hours. You're going to have 3.5 to upload. Well, this takes about 40 minutes, so no, this doesn't make up most of your final. How many questions will be on the exam? I don't know. I'm literally writing it on another screen. Like, one of the things, so exams are, by their very nature, they are timed evaluations, right? They are a statement of delivering knowledge within a set time period. So, especially in the online environment, one of the things that so I'm going to make an announcement about this. I wouldn't get overly upset if you don't finish the exam. Yeah, if you miss this completely, you would lose a considerable amount of marks. But what I would say is don't get overly upset if you don't finish the exam. I can't believe I'm having to tell this to students in second year. If you run into a problem that you don't know how to do, look at the next problem. Don't stare blankly at a problem for more than a few seconds. Move on. Come back to it if you have time. Move on. Do the problems you can do first, then go back and do the problems you can't do or you're struggling with. If this was an in-class examination, the exam would probably be shorter than it's going to be online. There's a couple of reasons for that. One is it's open book. 2 is longer exams discourage poor academic integrity because it literally takes time to cheat. And so if you're cheating, it takes time. And then you lose time, and then you don't finish your exam, and then you do poorly. So the exam might be difficult to finish in the time period. Make sure you upload. Don't freak out if you haven't been able to do all the questions. That's being taken into account with how the exam is going to be graded. So all questions are worth values, but we will be considering that we expect the exam to be a little bit longer. And I'm going to make an announcement to make it clear that the exam is on the long side. That is anticipated. Not completing the entire exam is not necessarily like a kiss of death and you're not going to get an A because you didn't finish the exam. You might still walk away with more or less 100%, even if you didn't finish the exam. It's just don't stare at questions you don't know how to do. Just move on. Because I've had that people going like, I didn't finish the exam because I couldn't figure out question 3. And I sat there looking at question 3 for 20 minutes. Like, why did you do that? If you can't get question 3, go to question 4. How can you do well? Because so I think one of the things to think about is if you're thinking in terms of absolute. Okay, so I think this is maybe one of the great disconnects. There's a way of thinking about grades where you come in with 100 and you lose grades over the term. I'm thinking you come in with 0 and you earn grades over the term. Like you've earned nothing until you've earned them. And so there are a total number of nominal points for this exam. But we then need to consider how everybody is performing. And so I don't curve the grades, but I consider the performance on the exam from the class. So like if the highest grade is 80 out of 100, let's say, then that's the highest grade in the class, and that gets awarded a really, really high grade. And then we rotate from there. So a curve fixes things to Gaussian. I do not fix things to a Gaussian curve. But what I do is that I don't take the nominal grade percentages necessarily. The nominal number is necessarily the total that the exam is out of when I calculate percentages. Yes, the exam will be identical to the midterm in how you upload things and do things. It will be identical to the midterm. Chitra, it's a fair question. So the only mechanism I have stated that you are not going to be responsible for, it is going to be on there. If you know it, there's part marks available if you screw stuff up, is ozanolysis. You will not be expressly asked to draw the mechanism for ozanolysis. There are going to be questions involving ozanolysis. They are going to say if you provide the wrong answer, you get 0. If you provide your work, you get part marks. Yeah, you'll be able to print all these questions off. You can print off anything you like. It's the same as the midterm. You print it, you take a picture, you upload it. There is no multiple choice. Yes, the exam will be designed to be completed in 3 hours, and you'll have 30 minutes to upload. The course material will be more mechanism heavy because I can evaluate all the earlier stuff through mechanism. Because everything we did previous to that comes into mechanism. So in mechanism heavy, will be chemistry heavy. This is from a previous exam. There will be something along these lines. It might not be quite the same size. Yeah, you also do not need to know the mechanism for boron reduction, Chitra. I didn't cover it because it's not really known. So you don't need to know the boron reduction mechanism because we don't know what it is. You can print these off. There's nothing stopping you printing these off, Jesse. So you can just download that. You can just copy paste into PowerPoint and print. You know what I'll give is just because of that, Jesse makes a good point. I'm going to add extra time. So we're going to make it 3 hours and 45 minutes instead of 3 hours and a half. So I'm giving an extra 15 minutes for printing off any questions you want to print off. So I'll make that announcement. Might not be a bad idea to print off your entire exam first and then take pictures and upload them as you go, because then if you hit the timeout and your time cuts off, you'll have the questions uploaded as you go. No, that's a fair point. I agree. I hadn't actually taken into account the printing off time, and a question like that does take forever to draw out. You're right. It makes sense to be able to print that off. I think you can right click as an image and copy and paste and print. Okay, so yeah, I know. Make sure you have ink if you're doing that. Please make sure you've got ink. I won't take my printer ran out of paper or ink as an excuse. Brenna, no, it's not. The reason I can't provide it as a single PDF is because not everyone has the same exam. It's massively randomized. It's not possible to do. Okay, so I think, how about we do a retrosynthesis with an Sn2 stereochemistry? So if you have that and you can't do that, so that's a very good point there, Katie, is if you don't have a printer, all the boxes will be numbered in something like this. I'll make sure I number them. And I have numbered them in the last couple of years. And then you can just write the letters and the structure. So you have like the numbers or the letters of the box. You just write what the structure is in each of those boxes. I agree. If you don't have a printer, it can be problematic. And there are major equity issues with this, and I get that. Okay. Let's see. Okay. Let's, so I've drawn one up there. Take a look, give a little thought into this. Okay, yeah, so no, so before I do that, I'm gonna point out, Chitra asked a question. Last time Blackboard only let you upload one picture, only let you upload one file. What you could do is you could make a short PowerPoint presentation, put 2 pictures in 2 slides, and then upload the PowerPoint. That was completely legitimate. I think I pointed that out in the instructions. So if what you want is you want to take a picture, stick it into PowerPoint, upload the PowerPoint, that's fine. And that's probably the fastest way to do it, if you have multiple pictures per slide. Or you could take the pictures and you can put them into a Word file and upload that. So there were ways to upload files that weren't individual pictures. Okay, Mohammed, the question you asked there is about something called an Sn2 Prime reaction. It's important. I didn't cover it. I'm not going to ask you it. So this question could ask you for, the way I've asked this is for retrosynthesis. So if I say provide a retrosynthesis, let's say that's what the question is, then what I'm not asking for is any reagents or any conditions. If I ask you to provide a synthesis, I'm asking for conditions and reagents. Because just go forward, you need to do that. Retrosyntheses are more conceptual. Sarah, yeah, you will be able to exit and enter the exam. You'll have full access to the exam. There's no time limit or number of entries. It's going to be open for you to enter and exit as you want. Yes. Yeah, sorry, Alan. I am going to make sure I've sent that announcement out. You're right, because that's an error from the, it's just a difference because of the NCAT thing versus this. Carbonyl chemistry is on this exam. Yes, it is on this exam. I will make an announcement for that just in case anyone saw the lectures and went, no, it's not. Yeah, no, it is. We covered it, and it's required part of the curriculum now. It's been withdrawn from other parts of the course, so we need to evaluate it here. Okay, so whenever in doubt, the first thing you should probably do is number your atoms. And if you're not in doubt on here, good for you, because I'm in doubt. So it's a really good idea to do this. And I'm doing it partially because I want to make sure I didn't screw up. Looks okay. Thanks, Jeanette. Gabriella, Jeanette answered the question. So we can sort of figure out what atoms are what. That simplifies it. That's worth marks right there, because it's already you've understood the framework of how this molecule is made. And now we need to figure out how to go backwards. HBr, then carbocation rearrangement, then form a ring. Well, we don't want a carbocation rearrangement because we don't want to move any carbons or hydrogens, and we haven't done any carbocation rearrangements in this course. We're going to pretend they don't happen because I would break everybody if I did that. So we're not going to talk about hydride shifts or carbocation rearrangements. If you've looked it up, and I think it mentions it in a textbook, great, good for you. I'm not going to ask you any questions that involve that because they're evil. But it's the right idea. It get you almost there, but not quite. So what we need to do functionally is I need to find some way to install bromine on 8 and ideally a leaving group on 6. I'm going to have thought this one out all the way. Okay, so open a ring, absolutely. For all of these, I draw because this is what I thought of in the spur of the moment, and I'm starting to think that I might have screwed myself. So we have that. And we can just say that, hey, let's make that a bromine. Doesn't the ring come from the line? No, yeah. So we're going backwards. So we've gone from ring, we've opened it, so we're going back towards the line. Yes, the ring comes from the line. No, yeah, let's say you don't need to open the ring, you need to close the ring. We're not using we're not going from ring to line, we're going from line to ring. So we don't need a reagent to open it, we need to close it. We're not creating a reagent to go backwards. We're just conceptually walking backwards. We are going in this direction. Okay, so we can get this. I was envisioning from that. But I'm not. So this example doesn't work because I'm not going to be able to get there. I was thinking it was going to be really clever and install bromines on both ends of this ring system. And technically, I think I can, because technically, if I add Br to this, so sorry, if I add it would do. Sorry, I'm going to do the 4. No, this works. This works. It's just weird. The most stable carbocation is the tertiary. I did not screw myself. This works. This is harder than a question I would give you, because that's kind of tricky. But it's relying on the fact of noticing that you can add dibromine to this. They're all the recordings are on YouTube. You can link from the syllabus. They're also all located under the files on this Teams channel, so you can get all of these. So we can add 2 bromines to this, and that would take us towards this product. And we can get to here, because if this can come from because we do a di-elimination, right? We're going to make this substitute double bond here, and then we'll do another double bond down there. We'll eliminate both the bromines, and of course we can get that from that by adding BR. Oh, the second BR here, where'd that go? It's there. They're still both there. It just got ring closed away. Okay. So what this question is basically asking you to do is walk functional groups around. It didn't actually end up doing what I wanted to do on the SN2. So I'm just going to skip ahead and do a quick SN2 question. I'm going to post this stuff immediately after class, along with anything that's not posted, that happens to not be posted, along with all the office hour material from the entire course. So you'll have everything that goes with all those videos. It's all BR the whole way through. There's no HBR at any point. Like, it's not radical. I'm just using BR, one's delta plus, one's delta minus. This is just pure ionic. Yeah, okay, thanks, Alyssa. Good, yeah. Okay. So I want to do a quick question on the SN2, because I think that was right. So let's just go over that. So again, let's say you have a system like this, and you treat this with iodine, I minus, lots of I minus. Then the nucleophile Katie, it's fair game. You don't need to know the precise numbers or anything, but you need to know the relative size. I don't care if you know the precise numbers. I couldn't care less. But yeah, the eclipse versus gauche versus staggered conformations is fair game. So this does an SN2, and SN2s involve an inversion of configuration. So how that's happening is, let's say my eye is down here looking at this, and I'm looking at it this way. Sorry, like actually, no, I'm looking at it straight on the way I am. I'm just rotating it 90 degrees. Then what I'm going to have is I'm going to have a methyl group up here. I'm just going to redraw this slightly. Bromine and hydrogen. So as my nucleophile comes in, it needs to come in anti-periplanar. Because again, if the orbital things make sense to you, there's a carbon-bromine bond. It's a sigma bond. And then there's the sigma star, and that is the weakest bond, which is the carbon-bromine bond, and that's going to be anti-bonding. And so the big lobe in the sigma star, this is where the nucleophile is coming. The nucleophile is trying to donate electrons to the sigma star. And if we look where the big lobe is, it's on the back of the bromine. And it's directly opposite the carbon. And so the nucleophile must come in 180 degrees away from the leaving group. Must. There's no other option. So if I'm looking at this, at some point the bromine starts elongating out. The ethyl group is going to be pointing straight out towards me. The hydrogen's down there. And we've kind of made a flat triangle. Everything is this carbon, this hydrogen are all in a plane. They're all perpendicular to my eyesight. The bromine's elongating out, the iodine is elongating in. And they're coming on opposite sides. Because they have to, because the iodine has to attack this big end of the back end, of the carbon. The iodine is coming in for the carbon, not the bromine, of course. And but that's opposite where the bromine is. It's 180 degrees to the bromine. There's an overall negative charge on here. And then this resolves itself. To give me that product. So I started with another way to draw it, just rotating this a bit. I started with that, and I've gone to that. And because in both these cases, the bromine and the iodine are the heaviest atoms present, they both have the 1 priority. The hydrogen is the 4 priority. The methyl group is 3. The ethyl group is 2. 2 is not 4. Note that the hydrogen is conveniently backing away from us in both these cases. This one is S. This one is R. We've gone from S to R. You have to be careful. It doesn't always, because sometimes when a nucleophile attacks, it's not the highest priority group, so you swap priorities around, but you always invert the stereocenter. It was one way, and now it is the other conformation. That is how Sn2s work. They always work that way. So Arian asked, if we were asked to draw mechanisms like this, would the arrows you show on the left suffice, or do we need to show the orbital drawings? You do not ever need to show the orbital drawings for this. I'm not going to ask you that. If they help you, I provide them because they tell you why it happens. This, if I asked you for the mechanism of this reaction, that would be full marks. The rest of the stuff, as I'm explaining it, this would be 2 out of 2. Okay. I think actually somebody else asked this question too. Or maybe Malit said you're coming back. No, it's you again. Okay. So I don't know if everyone can see Malitsa's question. If you want to pull it up from the chat. You know what? I realize that it doesn't get recorded that way, so I'm going to share my screen here. Oops. You can't see my screen. That is the final exam. I do not want to be sharing the final exam. Luckily, there was no shit. Okay. Well, all the questions that were on the page are getting deleted, and I am changing them. Good move, Trent. Real smart. Real smart. Okay, this is Melitza's question. Fuck my life. Okay, so the question was, looking down the indicated bond, draw the molecule in its lowest energy Newton projection, consider E2 reaction to draw the new double bond. The alkene will react for the lowest energy possible conformation, which you've just drawn. Is the resulting alkene near Z. So what this relied on is you drawing a Newton projection. Okay, so front carbon, methyl up, 2 hydrogens, back carbon, bromine left hand, terbutyl right hand, ethyl down. Now, is this the lowest energy projection? No, it's not. The two biggest groups are not opposite each other. They must be, so we have to rotate. In this case, I rotated the back carbon to get, or Melitza rotated the back carbon. Oh, this isn't my handwriting, it's too neat. To give the correct back carbon, the correct orientation. This is right. Then you must eliminate anti-periplanar because it is an E2 reaction. So you must take off the hydrogen she has circled in blue. You cannot take off the other one because it's an E2 and it reacts from the lowest energy conformation. So you generate a double bond. Then what happens basically is as you do that, everything else flattens out. So as you take off this hydrogen, this bromine, this carbon is going to stay where it is. This hydrogen is going to rotate down to make it flat. And it's going to overlap the terbutyl group, whereas this ethyl group is going to rotate up to make it flat because we're going to an sp2 center and they're going to be flat. So the ethyl group rotates up to be on the same side as the methyl group. The hydrogen rotates down to be on the same side as the terbutyl group. And that's kind of because if we're eliminating this, we're kind of pinching it together. So we pinch the other two together because that's what happens. So we should have the ethyl and the methyl on the same side. That is what's drawn with the terbutyl on the other side. So the E is the dominant double bond that is formed because it's the one you get from pinching these two together. It's determined by this hydrogen. We would have gotten a Z if the other hydrogen had been removed instead. But it's not. Do we only, is the rate law in the exam? Alyssa, you will not be asked to show rate laws. You might be asked about which reaction is faster, and that requires some understanding of rate laws. Okay, do we only consider antiperiplanar for E2 when wedges and dashes are shown? Do we always consider it? You always consider it. It might not be relevant if there are no wedges and dashes shown. Let me rephrase that. The way I'm thinking about it is it cannot be relevant if there are no wedges and dashes shown. How do I know it doesn't attack the other hydrogen? On the other carbon, you mean? Like on the ethyl group? Mostly because I told you. You're right. Like you're right. You're right, Melitza. I could theoretically. I just told you which one to look down. So I specifically defined the problem. It could, but it's just I told you what to do. I think this is all the miscellaneous grab bag and synthesis stuff, Noor. It's just where this is extra time. We've done some syntheses, we've done some retrosyntheses. So you walk through a bunch of examples. Yeah, Katie, because you can't tell, right? You don't know which way it rotates. If there's no representation of three-dimensionality, it's drawn in the right conformation as far as you know it's good. Dea, you would be answering a different question. Oh, sorry. Dea is saying, oh, can we do the other one? Yes. So Victoria, if there's stereochemistry and you did an SN1, you've lost stereochemistry at that center. So Victoria asked if there's stereochemistry in a molecule before an SN1, you do the SN1, do you put it back? No, you've lost it. You destroyed it. Now, if the stereochemistry elsewhere in the molecule, that was completely untouched. So that remains. So if you have a question that says, and I'm writing this right now in the exam, and I'm saying, basically the question saying, draw all possible diastereomers if you expect more or less equal amounts of those products. Draw both enantiomers if you expect a racemate. Draw the major product if you expect an enantioselective reaction. So I'm defining what to do. But in general, if I'm not saying that, I'm going to put this in the instructions. You just need to draw one representative. You don't need to draw both enantiomers. Okay, so I'm just going to do, I'm making sure I'm not showing any more of my exam. And I'm going to just do Daya's question here. Part of all the things I could have had on the screen. Because I'm recording this, so I know it's just so like if it wasn't up for long, but just in case anyone freeze frames it and takes a look. So what if it was the other one? I'm going to just share my screen. So I'm going to just take over and. And I don't have the exam on this computer, so this is fine. So we stripped the wrong proton from, this is the right proton to take, this is how this works. But Melitza correctly drew the Newman projection that you get directly from the conformation I had drawn. And that was this. So if we do the E2 from this not most stable Newman, we're going to strip this hydrogen, this bromine. We're going to pinch these two together, and we're going to pinch these two together. So we end up getting from this product is, should this be an ethyl or methyl? No, it's methyl. Methyl, terbutyl on the same side, hydrogen, and then ethyl and hydrogen. Whereas the product we got was methyl and ethyl on the same side, terbutyl on the same side as the hydrogen. This is the major. This is the minor. And if we're trying to assign E and Z, then, because that's what the question also asked, this is the biggest group on, sorry, this is the biggest group on this side of the double bond. This is the biggest group on that side. This is an E. Biggest group, biggest group. I messed something up, didn't I? I drew. Things are attached to the wrong carbons, sorry. Biggest group, same side set. Yeah, I just noticed that, Aaron. Yeah, yeah. Oh, so if you remove, so what they're saying is if I remove this hydrogen, I did a syn periplanar one. No, because actually that would, what would that do? Yeah, it would. It would. That just doesn't, that it isn't allowed, does not compute. Professor explodes. You can't take the gauche hydrogen and do an E2. Okay. Pinchy pinchy. if you try and do this with the model kit, you'll see that those kind of relax down into that, and they really don't have a choice. Like, these two are next to each other. Those two are next to each other. They're going to be Sn on double bond, cis on double bond to each other. It's just geometry. Okay, we're 2:35. I do need to run. I did intentionally schedule something after this so it didn't go too long. This is the end of the course. Yeah, this was also in a practice final, I believe. Or maybe the practice midterm. Probably the final. Yeah. I'm going to have office hours during course time on Friday, which is within my 24-hour blackout period. But I'm sort of holding a one-time special thing just to do that because it's fair. And I'm not available tomorrow because I'm out of town. And the exam is on the 11th, which I don't love because then there's no time to have like prep sessions beforehand. I know that SOS is doing something. I think they wanted me to post something and I didn't. Oops. Okay. So SOS has an exam prep session. I know the person who's running that. She's great. PALS is run by the same person. She's great. So use the resources. I think Samra is going to offer some extra office hours as well. That was last night. So PALS is today at 6:30. Use it if you can. Yeah. I don't make the exam schedule. This is insane. It's like your last course, and then like 2 days later you have an exam. Okay. Wish all of you the best of luck. Happy studying. Just breathe through the exam. Like, I know. Okay, Samra's got office hours 6 p.m. to 4 p.m. to 6 p.m. Samra will make an announcement about that on Blackboard. I've seen the same, like, first of all, I guess it's the last class. So I've got the same 40 to 50 to 60 of you guys coming in day after day in this. At the beginning of the course, I did say, you know, the #1 secret to success is keep up with this material. It's clear from the questions I'm getting here and just you guys coming in and making sure you're staying on pace with this, that you're keeping up with the material. I know that in general, the students with the highest anxiety are the highest performing students, because that's just the way it works. You're all type A's, you're all panicky and kind of freaked out, and it's your natural way of being. And normally that means you're putting in the work and staying up on this. You're going to do okay. Just keep breathing through it. There are always students who seem to think that you can learn by osmosis, like you're near the textbook and the information just travels from the textbook magically into your brain. Or if you go to class and fall asleep in the back, that magically is all just going to kind of sit in there. I know engagement's been really tough online. This has sucked. I kind of have liked this flipped format. I think I might be, you know, sending out an email to the class saying I'd like responses back from this versus just having the teaching thing, or if you're thinking this is way too much or how this works. But it's really hard for me to evaluate because I've done this online and it's not as much in person and the interaction's not been there and it's kind of been a shit show. And so I think this is more valuable. Those of you who have been engaging all the way through the semester, thank you. You've made this the best experience it could be under the circumstances. This is not this is not a good learning environment. And I know most of you have never actually had in-person, none of you have had in-person teaching at the university level. And it is night and day with this. Your professors are more engaged. You guys are more engaged. It's just it's a completely different thing. Online is just so disconnected. It's so inhuman. So thank you for participating. Okay, good luck, everybody. Have a wonderful break. Happy studying, and you have all almost survived the hardest semester of undergrad science. So just keep it. You're almost there. This is the hardest semester of undergrad science. Okay, bye.